Okay, good morning, ladies and gentlemen. Now today, we want to focus on the lecture of network errors and network error detections. So I want to see how we can identify the errors of the network and also how we can detect the errors of the network by using the specified and approved methods for doing that. Now, before we look at this topic in details, the errors and error detections, now let's look at the objectives of this chapter. At the end of this chapter, we must be able to identify the different types of noise commonly found in computer network and specify the different error prevention techniques and able to apply an error prevention technique to a type of noise. And also able to compare the different error detection techniques in terms of efficiency and efficacy, and perform simple parity and longitudinal parity calculations and enumerate their strengths and weaknesses. And also, we're going to cite advantages of arithmetic or checksum and cite the advantages of cyclic redundancy check and specify what type of errors cyclic redundancy checksum will detect. So people, these are our objectives of what we're going to discuss in this lecture. Now let's get started. Let's begin with defining what noise is. But before that, one thing that we need to understand is noise is always present. Noise is always present. In any communication, arrangement is interpreted. And from the previous lecture, we discovered that noise is a signal. But in this case, we don't want it. So any unwanted signal is called noise. And this is what you're saying is present all the time. So if communication line experience too much noise, the signal will be lost for it. That's the danger of it. The communication systems can check the transmission errors. Once an error is detected, the system may perform some actions that like to discuss further in this lecture today. So some system may perform no error control, but simply let the data and error be discarded. So they don't actually correct the errors now. If there is something that is not okay in the message, they simply discard the message. So there are two ways. Either the error is detected and controlled, or we can just ignore it. So now, let's put what is called white noise. What is white noise? White noise basically is also known as the family or portion. Collectively functioning in the field. So now, if the white noise gets too strong, it can completely disrupt the system. It's called white noise because something white you can see, something black you can see. There's something that can be detectable, and also if it gets too loud or too strong, then the signal is disrupted. Remember this, the signal to noise ratio. So if the noise power is too strong, you find that the signal will be lost. Now the white noise can be interpreted as follows. If you look at this first one here, you can see this is a normal wave where there's no noise. It's smooth like this. The lines and the peaks, okay, the lines and the peaks are very smooth and clear. When there's a bit of noise, little noise, you find that the lines and peaks are lines and peaks. But much noise distorts almost this power wave. So you can see that the noise has a negative effect on the message, and it's the one that causes network errors. So for what we call impulse noise, the impulse noise is very destructive because it is the noise that results in spikes of power that can destroy, okay, the transmission of information. Right? We cannot predict it. Okay, we cannot actually try to see when it is going to occur. Any spike in the power can actually disrupt the signal, or the maybe lightning from the sky can also cause impulse noise. So it is difficult to remove, okay, from an analog signal because it may be hard to distinguish from the original signal. So removing the impulse noise from analog signal is very difficult because both of them looks the same. But impulse noise can damage more bits if it actually affects the digital data. All right. So again, what you are saying is the impulse noise is difficult for all types of signals, either analog or digital. Look at what you're talking about. This here is some bit of noise. Okay, as you can see, the runs and the bits are not so clear. But observe here. This is what you call impulse noise. The rapid increase or change in power or transmission causes such things we are seeing here. So the effect of impulse noise from the data is very bad because the data is lost. Okay. So impulse noise, as you can see, there's low speed here in this data. When the noise, okay, comes, they expect that the data is disrupted. Look at the bits are completely lost in between here because of the impulse noise. So the impulse noise basically makes the transmission of digital data lose a lot of bits along the way. Okay. How about crosstalk? So that's what we call crosstalk in our data communication. So crosstalk also is unwanted coupling between two different signals. If it happens that two signals interfere each other, then that's what we call crosstalk. For example, hearing another conversation while talking on the phone, that's crosstalk, right? So relatively constant and can be reduced with proper measure. Otherwise, it is also another bad effect of signal. Look at this. Two people are communicating using different lines, but, all right, these lines are able to interfere with each other. So this is basically what we call crosstalk as we discuss crosstalk. All right. Now what about echo? What is echo? We know that from physics, okay, the reverberation of the signal. When the signal vibrates or bounces back, okay, as we transmit, that's what we call echo. So the effective feedback of transmitted signal as the signal moves through a medium is what we call echo. Most often occurs in quadrilateral cables, okay, where they only use one cable copper wire inside. So expect the reflective feedback as the data is actually moving. So if echo is bad enough, it could interfere with the original signal. Remember, you're trying to send data, and then there's reflective feedback coming from the other side. So if it is too strong, it will interfere with the original data, and that can cause network errors. Right. So look at this diagram here. It's trying to explain the effects of echo. There's this original signal being transmitted in the battery cable, but at the end there's reflective feedback, which we're calling echo. So now if this echo is too much, it can disrupt the message, and the message will be distorted. So echo is also another bad thing that we need to avoid in conclusion as we deal with the network signal errors. What about jitter? Right? What is jitter? So the result of small timing irregularities during the transmission of digital signal is what we call jitter. Now there's some specific time intervals that are set for a normal transmission. If you're sending data, you know every after 3 seconds, or it can be less than that, something has to be done. Movement of data has to be done in packets. But if that predefined amount of time that should be passed before you receive or send data, if it is not followed accordingly, some irregularities in the timing, we call that as jittering. Most likely, if, for example, you are watching a movie, you expect a smooth flow of signal to avoid the hang-ups, right? Now, when the signal is jittering, you find that there will be some breakups in this transmission. That's what you call jittering. That's the best example that you can use. So it is irregularities in terms of timing or data flow. So this can occur when a signal is repeated over and over. You find that it will jitter. So seriously, you find that jitters force a system to slow down the transmission, but there are steps that can be taken to reduce jitter. Right. For example, you're talking to someone, okay, we're asking someone a question, you expect him or her to respond okay, within a specified time. And somebody is trying to delay giving the response, okay, unnecessarily. That is what you can call jittering in real life situations. In this case, and in terms of signals, we are talking about the timing between the transmission of data from A to B and C to D, so on and so forth. So now look at this one diagram here. There's digital signal with no jitter. As you can see, it's just a more lines and peaks arrangement. But when there's jittering, you find that the lines are affected, the cables, okay, are not so regular. So this is what we call jitter, okay, transmission of data. There's jittering in the transmission of data, so that's not good. There's what we call also delayed distortion, okay, which occurs because the velocity of propagation of the signal through a medium varies with the frequency of signal. So find that there is delay which can cause distortion in the message, but it can be reduced. But there's also what we call attenuation, the continuous loss of signal strength as it travels through the loop. So every signal, that's why it needs a boosters, devices such as amplifiers, repeaters, and switch and so forth. These, they must repeat the signal when it is experiencing attenuation, the continuous loss of signal strength as it travels through. Right. Now let's talk about, we have talked about what we call errors in the network. Now let's talk about how we prevent such things in the app. So to prevent errors from happening, several techniques have been tried. So proper shielding of cables to reduce interference there to prevent that. Telephone lines, conditioning, authorizing, replacement order media on frequency of new one in case they are all back and forth, which can cause problems, jittering. Then proper use of digital repeaters, as I mentioned, amplifiers to avoid attenuation. These can also be applied to the signal. Now observe the static capacity of the media. In case the media is too small, sometimes it can cause delay. So all these techniques have been employed to reduce or mitigate the errors that you find in the internet. Now, there are kinds of errors that you have just listed. For example, white noise, impulse noise, crosstalk, echo, jitter, attenuation. How do you prevent white noise? It's summary. So install special filters for signals, okay, for analog signals, implement digital signal regeneration for the digital signal. So if there is noise in analog, you might filter the filter. If you're working with the digital signal, it's better you provide the means of regenerating the signal because that signal is lost. Then the impulse noise, again with analog, install filters that supposed to remove the noise. But for the digital signal, you must be able to have high quality processing signals to avoid impulse noise. Crosstalk, you must install proper shielding of the cables, right? Like the insulators in case of the culture cables and the shield, such as the mesh, aluminum mesh. So those can actually prevent error. Then for the but for echo, you must install proper termination of cables, right? Like for example, in the bus structure or the bus topology, where there's culture cable that is used as a main medium of sharing data, you put terminators, the things that will be discharging extra signals that you don't want, which will reverberate or come back as echoes. So you drop them down, drain them down. And then jitter, you use better quality electronic circuits with fewer repeaters, slow, okay, the transmission speed. So if the speed is too high, you find that you jitter, more especially if the microphone is not so good to the mouthpiece, you have jitter in the signals or output. So in other ways, how to avoid jittering when the microphone is not so good, you speak slowly. That's a technique that you can use. But also, you can also do the same in signal transmission if there is jittering, slow the transmission speed. Then the attenuation, install devices such as amplifiers, right? The switch to amplify the signals when there's continuous loss of what? Loss of data. Now let's talk about error detection apart from what you have seen, okay? Those techniques for preventing. Now I've got also techniques for detecting. So despite the best prevention techniques, errors will still occur. So to detect an error, something extra need to be added. This extra is an error detection code. So basically, there are 3 techniques for detecting errors. One to parity bit, arithmetic checksum, and cyclic redundancy checksum. So these are the techniques that we're going to discuss in this lecture. Now let's look at parity checks. If we're discussing the simple parity, we are talking about appending a 1 or a 0 depending on the type of parity you have, right? Look at this. If performing even parity, then add a parity bit such as 1 to make all the bits even. Otherwise, if the parity is odd, then you add a 1 to the numbers of ones to make them odd. So for example, you are sending 100100101 using the even parity. You experience that the number of ones in this data that you're sending, they are odd. So you have to make them even. So what do? You are going to add an extra 1 to this data here so that these can be even. The numbers of 1 can be even, right? So even this one here, how many ones are there? 1, 2, 3, 4. For this one, the numbers of 1 are already even. So in this case, you won't add a 1, because if you add a 1, they'll be odd. So you add a 0 to maintain the even parity. That's what this explanation here simply is. So the even parity, you endeavor that the number of ones in the data you are transmitting, they are even. In the odd parity, you endeavor that you have the number of ones which are odd. All right. So the principle is very easy there, people. Now, I've got what you call longitudinal parity, or sometimes you call it block parity, whereby you consider the columns and the rows as you do your detection methods. So in this case, you add the parity bit to each character in the column, and also you do the same for each character in the row. For example, this you've got 3 rows here, so you do the parity for each column. You do the parity for each column. So in this case, perhaps we are considering even parity, because if you look at these ones are already even, that's why there's 0 there. So these ones are 3, so it's odd number, so that's why I'm putting 1 there. So this and that continues up to this point. And you also do in the row manner. So how many are these ones? 1, 2, 3, 4, 5. So make them even, add a 1 there. So as you can see, all these you also do the same. All these you also do the same, just like that. And you must have a special by if you do this parity, then you must give it 0. And if you check also even parity for this, you must give it 0. So this is called block parity, or sometimes we call it longitudinal parity. It's also very, very impressive for, let's say, more than one error detection that you have considered. Maybe, for example, for 2 error detections, the longitudinal works very well, right? So as it actually explains in this case, it talks about what happens if there are problems with what? The bits in the rows or the columns, right? So both simple parity and longitudinal do not catch all errors, because the simple parity catches only 1, and then the longitudinal catches what you call multi-bit errors, right? But what about if you have burst errors? A lot of errors happen at the same time. So that's where now you need techniques such as the checksum. So the checksum is used in TCP, IP, internet protocols, and has been very, very effective technique for catching the burst errors in the signal. So how do you do it? So you convert all the data that you have, which is in binary, take them to extend and add them. That's why it's called checksum, add. But remember, these numbers have got only 2 digits, as you can see. So when you add them, the leading digit, you remove it. and you're going to add it to the remainder like this. So going to be, okay, it's going to be 10 plus these 2 here to give you 12. So this 12, in this case, is your checksum, right? Of course, if you're working with the ones and zeros, of course, there's the element of taking them to first complement so that you can have a very secure checksum technique for catching the errors. Right, I like this technique, it's very good. But wow, there's also another more powerful technique called Cyclic Redundancy Checksum, or CRC. So this one detects, okay, it's a detection method that treats the packet of data to be transmitted as a large polynomial. So if you've forgotten a polynomial technique in mathematics, this is the time that you do a bit of revision, because this technique is about that. But don't worry, for programs that embed all those techniques in one function. So just a matter of using those programs and code them and use them, they're going to benefit from the detection, okay, powers of this method. So the message, okay, is transmitted to the receiver, which is the reminders. So the receiver divides the message and the reminder by the same generating polynomial. So if the remainder not equal to 0 results, there was no error during transmission. If the remainder of 0 results, there was no error in the transmission. So what we're saying is, if the remainder not equal to 0, there was an error during transmission. If the remainder of 0 results, there was no error in this place. So this is the pseudocode or the algorithm of how this method works, right? So for example, some standard generating polynomials, this is for example for CRC4, okay, that is the highest order of bits, 4. So you discover that you're going to have polynomial in this line. The polynomial will be done in this line, so on and so forth. So this technique will help you to create a polynomial expression, which you can actually simplify by using the division technique. All right, as you can see from here. Right? So now what is a summary? What we've discussed is noise is always present in computer networks, and if noise level is too high, errors will be introduced during the transmission. That is a fact. The types of noise, that includes white noise, impulse noise, crosstalk, echo, jitter, and also attenuation can be also amongst the noise. And of course, other techniques that can reduce noise, like shielding the cables, or conditioning the lines, or use equipment that can boost signals, such as repeaters and also amplifiers. All these can prevent the noise. But what about detecting? We have seen that to detect an error, you need to use techniques such as parity bit, or you can use arithmetic checksum, or the most powerful one, the cyclic redundancy checksum. All these techniques are very good because they help you to detect the errors in the message and to report back that the message that I've received is not the one that was intended to come here. So you find that with these techniques, there's some guarantee that what is received on the other end is what was intentionally sent by the source computer. So basically, people, we actually benefit so much from these techniques that we have looked at, the prevention techniques and the detection techniques. Okay, so as you go through this lecture, people, I encourage you to pay attention to what errors are and how to prevent them and how you detect them as you work with computer errors. Right, so people, see you next time as we look for more topics in data communication and networking. Bye-bye.